The Hawaii hotspot is a volcanic hotspot located near the namesake Hawaiian Islands, in the northern Pacific Ocean, one of the most well-known and heavily studied hotspots in the world. The Hawaii plume is responsible for the creation of the Hawaiian Emperor Seamount chain, a chain of volcanoes over 5,800 kilometers long. 4 of these volcanoes are active, 2 are dormant, and more than 123 are extinct, many having since been ground beneath the waves by erosion as seamounts and atolls. The chain extends from south of the island of Hawaiʻi to the edge of the Aleutian Trench, near the eastern edge of Russia. While most volcanoes are created by geological activity at tectonic plate boundaries, the Hawaii hotspot is located far from plate boundaries. The classic hotspot theory, first proposed in 1963 by John Tuzo Wilson, proposes that a single, fixed mantle plume builds volcanoes that then, cut off from the source by the movement of the Pacific plate, become increasingly inactive and eventually erode below sea level over millions of years. According to this theory, the nearly 60 degrees bend where the Emperor and Hawaiian segments of the chain meet was caused by a sudden shift in the movement of the Pacific plate. In 2003, fresh investigations of this irregularity led to the proposal of a mobile hotspot theory, suggesting that hotspots are mobile, not fixed, and that the 47-million-year-old bend was caused by a shift in the hotspot's motion rather than the plates. Ancient Hawaiians were the first to recognize the increasing age and weathered state of the volcanoes to the north as they progressed on fishing expeditions along the islands. The volatile state of the Hawaiian volcanoes and their constant battle with the sea was a major element in Hawaiian mythology, embodied in Pele, the deity of volcanoes. After the arrival of Europeans on the island in 1880 to 1881, James Dwight Dana directed the first formal geological study of the hotspot's volcanics, confirming the relationship long observed by the natives. 1912 marked the founding of the Hawaiian Volcano Observatory by volcanologist Thomas Jagger, initiating continuous scientific observation of the islands. In the 1970s, a mapping project was initiated to gain more information about the complex geology of Hawaii's seafloor. The hotspot has since been tomographically imaged, showing it to be 500 to 600 kilometers wide and up to 2,000 kilometers deep, and olivine and garnet-based studies have shown its magma chamber is approximately 1,500 degrees Celsius. In its at least 85 million years of activity, the hotspot has produced an estimated 750,000 cubic kilometers of rock. The chain's rate of drift has slowly increased over time, causing the amount of time each individual volcano is active to decrease. From 18 million years for the 76-million-year-old Detroit seamount, to just under 900,000 for the 1-million-year-old Kohala. On the other hand, eruptive volume has increased from 0.01 cubic kilometers per year to about 0.21 cubic kilometers. Overall, this has caused a trend towards more active but quickly silenced, closely spaced volcanoes, whereas volcanoes on the near side of the hotspot overlap each other. The oldest of the Emperor seamounts are spaced as far as 200 kilometers apart. Theories. Tectonic plates generally focus deformation and volcanism at plate boundaries. However, the Hawaii hotspot is more than 3,200 kilometers from the nearest plate boundary. While studying it in 1963, Canadian geophysicist J. Chuzo Wilson proposed the hotspot theory to explain these zones of volcanism so far from regular conditions, a theory that has since come into wide acceptance. Wilson's stationary hotspot theory. Wilson proposed that small, long-lasting, exceptionally hot areas of magma exist under the Earth's surface. These heat centers create thermally active mantle plumes, which in turn sustain long-lasting volcanic activity. This mid-plate volcanism builds peaks that rise from relatively featureless seafloor, initially as seamounts as later as fully fledged volcanic islands. Plate tectonics cause the local tectonic plate to slowly slide over the hotspot, carrying its volcanoes with it without affecting the plume. Over hundreds of thousands of years, the magma supply for the volcanoes slowly cut off, eventually going extinct. No longer active enough to overpower erosion, the volcano slowly sinks beneath the waves, becoming a seamount once again. As the cycle continues, a new volcanic center manifests, and a volcanic island arises anew. The process continues until the mantle plume itself collapses. This cycle of growth and dormancy strings together volcanoes over millions of years, leaving a trail of volcanic islands and seamounts across the ocean floor. According to Wilson's theory, the Hawaiian volcanoes should be progressively older and increasingly eroded the further they are from the hotspot, and this is easily observable. The oldest rock in the main Hawaiian Islands, that of Kauai, is about 5.5 million years old and deeply eroded, while the rock on Hawaii Island is a comparatively young 0.7 million years of ageless, with new lava constantly erupting at Kilauea. The hotspots present center. Another consequence of his theory is that the chain's length and orientation serves as a record direction and speed of the Pacific Plate's movement. A major feature of the Hawaiian Trail is a sudden 60 degrees bend at a 40 to 50 million-year-old section of its length, and according to Wilson's theory, this is evidence of a major change in plate direction, one that would have initiated subduction along much of the Pacific Plate's western boundary. This part of the theory has recently been challenged, and a bend might be attributed to the movement of the hotspot itself. Geophysicists believe that hotspots originate at one of two major boundaries deep in the Earth, either a shallow interface in the lower mantle between an upper convecting layer and a lower non-convecting layer, or a deeper D layer, approximately 200 kilometers thick and immediately above the core mantle boundary. A mantle plume would initiate at the interface when the warmer lower layer heats a portion of the cooler upper layer. This heated, buoyant, and less viscous portion of the upper layer would become less dense due to thermal expansion, and rise towards the surface as a Rayleigh-Taylor instability. When the mantle plume reaches the base of the lithosphere, the plume heats it and produces melt. This magma then makes its way to the surface, where it is erupted as lava. Arguments for the validity of the hotspot theory generally center on the steady age progression of the Hawaiian Islands and nearby features. A similar bend in the trail of the McDonald hotspot, the Austral Marshall Islands seamount chain, located just south. Other Pacific hotspots following the same age progressed trend from southeast to northwest in fixed relative positions, and seismologic studies of Hawaii which show increased temperatures at the core mantle boundary, evidencing a mantle plume. Shallow hotspot theory. Another hypothesis is that melting anomalies form simply as a result of lithospheric extension, which allows pre-existing melt to rise to the surface. These melting anomalies are called hotspots in plume theory, but this name presupposes the mantle source is unusually hot, a feature that has not been confirmed by observation. In the case of the Emperor Hawaiian seamount chain, the Pacific Plate plate boundary system was very different at tilde when the Emperor Seamount chain began to form. There is evidence that the chain started on a spreading ridge that has now been subducted at the Aleutian Trench. The locus of melt extraction migrated off the ridge and into the plate interior, leaving a trail of volcanism behind it. This migration may have occurred because this part of the plate was extending in order to accommodate intraplate stress. Thus, the long-lived region of melt escape was sustained. Seismic tomography does not support the plume hypothesis, notwithstanding the numerous papers that have been published citing seismological evidence for a plume in the region. These proposed plumes are all in different places, many of them tilting at high angles and in different directions, and some of them thousands of kilometers from the Big Island. No reliable image of a mantle plume extending down to the core mantle boundary has been obtained. Moving hotspot theory. The most heavily challenged element of Wilson's theory is whether or not hotspots are indeed fixed relative to the overlying tectonic plates. Drill samples, collected by scientists as far back as 1963, suggest that the hotspot may have drifted over time, at the relatively rapid pace of about 4 centimeters per year during the late Cretaceous and early Paleogene eras. In comparison, the mid-Atlantic ridge spreads at a rate of 2.5 centimeters per year. In 1987, a study published by Peter Molnar and Joanne Stark found that the hotspot does move relative to the Atlantic Ocean. However, they interpreted this as the result of the relative motions of the North American and Pacific plates rather than that of the hotspot itself. In 2001, the Ocean Drilling Program, an international research effort to study the world's seafloors, funded a 2-month expedition aboard the research vessel JOIDES Resolution to collect lava samples from 4 submerged emperor seamounts. The project drilled Detroit, Nintokus, and Koko seamounts, all of which are in the far northwest end of the chain, the oldest section. These lava samples were then tested in 2003, suggested a mobile Hawaiian hotspot on a shift in its motion as the cause of the bend. Lead scientist John Tarduno told National Geographic, the Hawaii bend was used as a classic example of how a large plate can change motion quickly. You can find a diagram of the Hawaii Emperor Bend entered into just about every introductory geological textbook out there. It really is something that catches your eye. Despite the large shift, the change in direction was never recorded by magnetic declinations, fracture zone orientations or plate reconstructions, nor could a continental collision have occurred fast enough to produce such a pronounced bend in the chain. To test whether or not the bend was a result of a change in direction of the Pacific plate, scientists analyzed the lava samples' geochemistry to determine where and when they formed. Age was determined by the radiometric dating of radioactive isotopes of potassium and argon. Researchers estimated that the volcanoes formed during a period 81 million to 45 million years ago. Tarduno and his team determined where the volcanoes formed by analyzing the rock for the magnetic mineral magnetite. While hot lava from a volcanic eruption cools, tiny grains within the magnetite align with the Earth's magnetic field and lock in place once the rock solidifies. Researchers were able to verify the latitudes at which the volcanoes formed by measuring the grains' orientation within the magnetite. Paleomagnetists concluded that the Hawaiian hotspot had drifted southward sometime in its history, and that, 47 million years ago, the hotspot's southward motion greatly slowed, perhaps even stopping entirely. History of study. Ancient Hawaiian. The possibility that the Hawaiian Islands became older as one moved to the northwest was suspected by ancient Hawaiians long before Europeans arrived. During the voyages, seafaring Hawaiians noticed differences in erosion, soil formation, and vegetation, allowing them to deduce that the islands to the northwest were older than those to the southeast. The idea was handed down the generations through the legend of Pele, the fiery Hawaiian goddess of volcanoes. Pele was born to the female spirit Haumea, or Hina, who, like all Hawaiian gods and goddesses, descended from the supreme beings, Papa, or Earth Mother, and Waka, or Sky Father. According to the myth, Pele originally lived on Kauai when her older sister Namaka, the goddess of the sea, attacked her for seducing her husband. Pele fled southeast to the island of Oahu. When forced by Namak to flee again, Pele moved southeast to Maui and finally to Hawaii, where she still lives in the Halemaumasu crater at the summit of Kilauea. There she was safe, because the slopes of the volcano are so high that even Namaka's mighty waves could not reach her. Pele's mythical flight, which alludes to an eternal struggle between volcanic islands and ocean waves, is consistent with geologic evidence about the ages of the islands decreasing to the southeast. Modern studies. Three of the earliest recorded observers of the volcanoes were the Scottish scientists Archibald Menzies in 1794, James McRae in 1825, and David Douglas in 1834. Just reaching the summits proved daunting. Menzies took 3 attempts to ascend Mauna Loa, and Douglas died on the slopes of Mauna Kea. The United States exploring expedition spent several months studying the islands in 1840 to 1841. American geologist James Dwight Dana was on that expedition, as was Lieutenant Charles Wilkes, who spent most of the time leading a team of hundreds that hauled a pendulum to the summit of Mauna Loa to measure gravity. Dana stayed with missionary Titus Cone, who would provide decades of first-hand observations. Dana published a short paper in 1852. Dana remained interested in the origin of the Hawaiian Islands, and directed a more in-depth study in 1880 and 1881. He confirmed that the island's age increased with the distance from the southeasternmost island by observing differences in the degree of erosion. He also suggested that many other island chains in the Pacific showed a similar general increase in age from southeast to northwest. Dana concluded that the Hawaiian chain consisted of 2 volcanic strands, located along distinct but parallel curving pathways. He coined the terms low and Kea for the 2 prominent trends. The Kea trend includes the volcanoes of Kilauea, Mauna Kea, Kohala, Haleakala, and West Maui. The low trend includes Eloihi, Mauna Loa, Waialae, Kehoolo, Lana'an, and West Molokai. Dana proposed that the alignment of the Hawaiian Islands reflected localized volcanic activity along a major fissure zone. Dana's Great Fissure theory served as the working hypothesis for subsequent studies until the mid-20th century. Dana's work was followed up by geologist C. E. Dutton's 1884 expedition, who refined and expanded Dana's ideas. Most notably, Dutton established that the island of Hawaii actually harbored 5 volcanoes, whereas Dana counted 3. This is because Dana had originally regarded Kilauea as a flank vent of Mauna Loa and Kohala as part of Mauna Kea. Dutton also refined others of Dana's observations, and is credited with the naming of Ae and Pahoeho-type lavas. Although Dana had noted a distinction, stimulated by Dutton's expedition, Dana returned in 1887, and published many accounts of his expedition in the American Journal of Science. In 1890 he published the most detailed manuscript of its day, and remained the definitive guide to Hawaiian volcanism for decades. 1909 saw the publication of two large volumes which extensively quoted from earlier works now out of circulation. In 1912 geologist Thomas Jagger founded the Hawaiian Volcano Observatory. The facility was taken over in 1919 by the National Oceanic and Atmospheric Administration, and in 1924 by the United States Geological Survey, which marked the start of continuous volcano observation on Hawaiʻi Island. The next century was a period of thorough investigation, marked by contributions from many top scientists. The first complete evolutionary model was first formulated in 1946 by USGS geologist and hydrologist Harold T. Stearns. Since that time, advances have enabled the study of previously limited areas of observation. In the 1970s, the Hawaiian seafloor was mapped using ship-based sonar. Computed SYNBAPS data filled holes between the ship-based sonar bathymetric measurements. From 1994 to 1998, the Japan Agency for Marine Earth Science and Technology mapped Hawaii in detail and studied its ocean floor, making it one of the world's best-studied marine features. The JAMSDEC project, a collaboration with the USGS and other agencies, utilized manned submersibles, remotely operated underwater vehicles, dredge samples, and core samples. The SIMRAD EM300 multi-beam side-scanning sonar system collected bathymetry and backscatter data,